Hello students, welcome to BW Gulf and I hope all of you are doing good. So welcome, and today we are going to talk about magnetic effects of electric current. I am Tanya and I believe all of you remember me. So we have done summaries and one-shots and recaps of your chapter, right? Light reflection and refraction, electricity, the human eye and the colorful world. This is your last in the fourth chapter in your physics, and we are going to have a recap of the whole chapter in a very easy, crisp manner. So take out your paper and pencil and be ready with the paper and pencil, because yes, this chapter, very easy chapter, very small chapter, we are going to wrap it up in no time. Okay, so talking about magnetic effect of electric current. Yes, everyone, whenever we talk about electric current, there are certain effects we see. What are they? Let's say heating effect. I hope all of you remember. Then we have chemical effect. The third effect is nothing but your magnetic effect, the term. Okay, first of all, we are going to understand what is a magnet. Then, yes, what is magnetic field? Of course, we are going to talk about, yes, magnetic field there in a conducting wire, or yes, conductor, current conducting or current carrying conductor. All these things we are going to do. So, let's start with the basic, everyone. The first thing that is there, it is nothing but our magnet, term magnet. What exactly a magnet is? In class 6th we studied. The first thing, no? Yeah. Fun with magnets, this was the chapter. And yes, in class 6 we studied about a magnet, that what exactly a magnet is. So if I tell you a magnet, a substance that will attract or repel magnetic material. Talking about magnetic material, everyone, yes, material having nickel, cobalt and iron in them. Okay, so basic definition will be a material, a substance that will attract or repel what? Magnetic material or any material made up of iron, nickel, cobalt. Okay, so yeah, now if I say that, okay, this is a general definition that we have. Talking about, yes, if you observe a magnet, you will see that whenever any magnetic material is brought closer to a magnet, brought closer to that substance, no, it will, the magnet or the object certainly over there, if I say that, okay, this is a magnet, yeah, now, yes, it will have a region. Okay, moreover, magnets, they undergo a property of magnetism, that is nothing but attraction and repulsion. Right? This is our basic information that we have regarding magnet. So everyone, yes, magnet is a basic substance that will undergo attraction and repulsion. Moreover, attract magnetic material. What are magnetic material? Materials made up of iron, nickel, cobalt, having iron, nickel and cobalt in them. Right? Now, if I ask you how many type of magnets you know, you can talk about bar magnet, horseshoe magnet, disc magnet, compass needle, magnetic compass needle. These all are our magnets only. Examples, right? We are starting from the scratch, everyone. Yeah. Now, moving forward, when I talk about properties of a magnet, so you all know that yes, our magnets, they are dipole in nature. So everyone, very important point over here, dipole. What do you mean by that? Dipole, that means two pole. Yes, two ends of a magnet, we are going to call them as north pole, south pole, certainly dipole. Di means two, pole, of course, pole. Yeah, now have a look over here. So yes, dipole in nature, one will be north, the other one is going to be south. Pretty much easy, right? Now, if I will suspend a magnet, what will happen? After suspending a magnet, I will observe magnet is always aligned into north and south direction. So yes, very important thing. A magnet will rest or magnet will align itself when? Not touch, suspended freely in north-south direction. The north pole of my magnet will point towards geographic north. Okay, south pole of the magnet will point towards, yes, geographic south. That is why the name is there, no? Yeah, north pole, south pole. So when we talk about the north pole of the magnet pointing towards the north of the earth, geographic north. Similar way, south pole pointing towards the geographic south. Okay, in higher standards, you will be made aware that in 12th probably, yeah, you will be made aware that this north pole is nothing. See, north pole of a magnet is nothing but north seeking pole, the proper name. Yeah, class 12 concept is I'm sharing a bit of information with you. Similar way, south pole, south seeking pole. Okay, last thing everybody knows, yes, magnet will undergo the property of magnetism, that is attraction and repulsion. Attraction and repulsion will take place between what? Yes, your poles. So, like pole, everyone, talking about like pole, that means same. Yeah, North Pole and North Pole, South Pole and South Pole, they will of course repel, move away. Talking about unlike pole, what will happen with unlike pole, everyone? Unlike, yeah, not same, not similar, different. That means north and south. What will happen here? Of course, attraction, they will come closer. Okay, attraction, repulsion, this is nothing but basic of a magnet. Yes, we know about magnets, so this is nothing but normal, basic that we can talk about. Now, moving forward, as I am telling you, yes, there is a magnet. Magnet will have a particular region. In that particular region, if any other magnetic material will come, of course, we can see attraction and repulsion. So, everyone, when we talk about magnet, the area around the magnet has been given a special name. Okay, so when you talk about magnetic field, can you actually imagine field, right? Yeah, the area, the region, magnetic field. Yes, the field, the region, the area around a magnet. Okay, what will it do? What actually we are seeing over here? Yes, it is nothing but the area around the magnet that will influence the magnet. What do you mean by influencing the magnet? What can a magnet actually do? Okay, you tell me, what can a magnet actually do? Attraction or repulsion? Yeah, that is the maximum thing a magnet can do. Right? Certainly you will see more things also, but yeah, in general sense. So, this region will influence the magnet in a way. Okay, that is why I'll call this region as magnetic field. Okay, now, imagine, have a look on the picture over here. There is a magnet and I am keeping this magnet over shavings of iron. Okay, tiny pieces of iron. The moment I'll keep this magnet, there on the shavings of the iron, first thing that I will observe that yes, some of the iron pieces, they are getting attracted onto the magnet. Maximum at the ends. Okay, then I will see that, okay, there is a pattern, circular sort of pattern getting formed onto the paper where these iron filings are. So, yes, these pattern, this shape, it is actually giving me one information. What information it is giving me? That yes, this particular scenario is telling me that, okay, magnetic field. Okay, the representation, now everyone, see, it becomes very difficult for us to talk about a thing that we haven't seen. Yeah, so if I will say that, okay, I am talking about, let me say, one of my relatives, and you have not seen my relative. So certainly you will hear me out, but you won't be able to imagine that, okay, ma'am's relative, somewhat like this. Yeah, so similar way, if I'm talking about magnetic field, right, and you have not seen magnetic field, you cannot see magnetic field as such. Yeah, but if I need to talk about it in a better manner, in a representable manner, things would be more understandable to you. That is why when we talk about magnetic field lines, yeah, they are nothing but yes, the represented form of your magnetic field. By using magnetic field lines only, we are confident that okay, we are talking about magnetic field. Okay, so whenever a person asks that okay, what is the importance? Why talk about magnetic field lines? See, in order to get a better representation, okay, how my magnetic field looks, moreover, what is happening, yes, magnetic field is important. Okay, now I am talking about magnetic field, right? A lot. Certainly, we are going to specify magnetic field. Everyone, whenever we will talk about, yes, you can talk about magnetic field, certainly. So, when we talk about magnetic field, the symbol of magnetic field is B. Okay, with B symbol, we represent it. Yeah, of course, you can talk about the magnitude, that means the strength, how much magnetic field is there, we can. Okay, similar way, you can talk about the direction of the magnetic field. Okay, where, from where to where? Yeah, so whenever we will talk about magnetic field, it has both magnitude and direction, and we will see that. Okay, we are going to talk about that. Yeah, so if I say magnetic field, everyone, magnitude is there, yes, strength is there, of course it is there, direction is there, of course it is there. So magnetic field will be a scalar quantity or vector quantity? Of course a vector quantity. Alright, now talking about magnitude, talking about direction, there will be a unit, right? There will be SI unit. So all of you talking about the SI unit. Yeah, it is nothing but Tesla. Okay, capital T symbol. Yeah, B is the symbol of magnetic field. Okay, now please don't get confused. Okay, unit, SI unit, Tesla. Yeah, now of course I believe all of you know about Nikola Tesla, right? A very great scientist. Yeah, of course more discussion we can do in the coming up sessions as well, but by far now I believe till here clarity is there. Okay, now moving ahead, we have basic about magnetic field. We can talk about magnetic field lines also. Now, how the direction, how their movement, what will happen. So we are going to talk about our characteristics of magnetic field lines. Okay, I am telling you direction is there. Of course, direction is there. I am telling you strength would be there. Of course, strength is there. So, what basic information my magnetic field lines can give if I take up a bar magnet? Okay, take up a bar magnet, everyone. Okay, North Pole and South Pole. Yeah, my magnetic field lines, okay, yes, they will be represented in closed loops. No break will be there. First, very important thing, closed loops. Yeah, I hope you all are aware about loops, right? There won't be any starting and ending point. Loop. Okay, so yes, for representation purpose, we are depending on closed loops. There won't be any starting ending point. Moreover, no break. Okay, now closed loops as such, right? What about the direction? From where to where? Certainly, whenever we talk about direction, yes, your magnetic field line, okay, they will emerge. Let me use a better color for you. Okay, they will emerge. Emerging means coming out. Yeah, they will emerge from the North Pole. Okay, and enter the South Pole. Okay, now have a look from north to south. Okay, like closed loop like this. Yeah, let me make it from north to south. Okay, now see outside is from north to south. Okay, ma'am, closed loop. But when I will close this whole scenario, have a look over here. When I close this, can you see inside it is from south to north? Yeah. Okay, closed curve, closed loop, yes, emerging from north to south. Let me just make it proper. Yeah, okay, everyone. Alright, so one thing is very clear, that is closed loop with no breaks. Moreover, emerging from north and like this, okay. So if I say, I believe this is okay. Okay. So yes, you can refer the diagram. Don't look onto my drawing. It is not that great, but yeah. Okay, bar magnet. Similar way with horseshoe magnet also. You cannot say now only for bar magnet. No, similar way for horseshoe magnet also. Okay, if I'm talking about magnetic field lines, so yeah, I'm considering all. Yeah, so first thing clear, closed loops, closed curves, and of course emerging from the North Pole and merging to the South one. Inside the magnet, yes, south to north. Okay, yeah, now very clear, and the thing that is evident, have a look over here only. Okay, let's see over here. So if I talk about the strength, everyone, yeah, magnitude, strength, no, we have to. So when I talk about the strength, all of you only imagine if the magnetic field lines are very close by, their strength will be more. Yeah, and the wider the magnetic field lines move, of course the strength is going to decrease. Similar thing happens, yes, everyone. So your degree of closeness of the field lines, they only determine the relative strength. Closer magnetic field line, stronger the magnet. Yeah, yes, of course magnitude would be more. Okay, field strength is more. Stronger the field. So everyone, more crowded the line, stronger the field. Very important point. Very important point. Okay, now we have basic understanding. Now, let's say I am talking about a magnetic field. Okay, now this is my magnetic field. Okay, like, okay, direction. Yeah, I want to find out the direction on this magnetic field, but at a particular point. Listen to my question, everyone. Okay, my magnetic field is given. Yeah, I want to find the direction. See, I can see the whole direction as well, but I want to find out the direction at this particular point only. I am curious. So, what will I do? Simple, draw a tangent. At this particular point on my magnetic field, certainly the direction is here. Clear? Right? So, yes, we use this tangents in order to find the direction of the magnetic field at a particular point on the magnetic field itself. Okay, last thing will be that if my lot of closed loops are there, what will happen when two magnetic field lines, they are going to intersect? What will happen then? Yeah, have a look at crossing over. If I say like this, crossing over, what will happen? Okay, let's say like this. So, in this particular scenario, everyone, whenever, yes, my two magnetic field lines, they intersect, no, yes, you cannot talk about the direction at that particular point because there will be two tangents and two different directions. So, this cannot happen. Okay, so in this particular case, moreover, in the standard form as well, magnetic field lines, they do not cross each other. They certainly cannot. Then we will have two directions. It will become very difficult for us to understand. Yeah, not at all possible. Okay, so 4 general points we have. We know closed curves, of course, closed curves, moreover, no breakage. Second thing will be moving from the north, entering the south, and inside the magnet, south to north. Okay, third thing will be closer the magnetic field lines, more the strength. Imagine crowded. Yeah, more the strength. Last one will be whenever, if two magnetic field lines, they cross over each other, they intersect. Yes, you cannot find out the direction at all, and certainly they cannot cross over. There will be two directions. It would become difficult for us. Okay, basics about magnetic field lines. Now, as we are having basic understanding of magnetic field line, we are going to implement this thing onto, yes, some experiment. So, what happened? Now, how the picture turned? Kids, we talk about this ostrich experiment, no, in our class 7th as well. We have heard of it. Yeah, there was a scientist in 1820, Hans Christian Ostrich. He said that, okay, I'm working on a circuit. Yeah, he was normally working on a circuit and current was flowing through the circuit. On his table, a magnetic compass was there. Now, what happened? He observed that when current is flowing through a wire, a conducting wire, yeah, he saw that the compass needle is deflecting. Okay, kids, when my compass needle can deflect? My compass needle is a magnet. My compass needle is going to deflect if there is a magnet nearby. Then only your compass needle will deflect, else it won't. Yeah, it is going to show the direction only. No, it is aligning itself to the earth. Okay, so he was very much curious that, okay, initially it was showing north and south. Now suddenly my compass needle is deflecting when I am allowing the current to pass through the circuit. Have a look over here. North-south initially. Okay, current passing through the whole circuit. Yeah, compass needle kept nearby. Compass needle deflecting. Strange. Now, from this scenario only, yes, he took out ample of observations and he stated what he stated. He said that when your current is going to pass through a wire, a conducting wire, and you're going to keep a compass needle next to it, right? The compass needle is going to show deflection. Moreover, he accidentally discovered this thing. Okay, certainly he stepped up and talked and he showed that electricity and magnetism, they are related. They are not, in a way far apart from each other. So from this experiment, he talked about magnetic effect of electric current. Magnetic effect of electric current. Because of electric current, some magnetic effect is we are able to observe that. Okay, so he coined that yes, electricity and magnetism, they are related formula. Okay, phenomena. Right, and yes, he only, see, wire is there, current is going through the wire. Yeah, certainly over here, if and only if this wire is behaving like a magnet, then only my compass needle will deflect. No. Else why? Or if this wire is actually able to form magnetic field lines, the region around it, then only the magnetic needle is going to deflect, right? Else what? Else it won't. Initially it was not. Yeah, certainly over here, what is happening when electric current is passing through the wire? Of course, magnetic field lines. Yeah, let me just make them properly. Okay, like concentric ones. Okay, it is getting formed. As magnetic field lines are getting formed, of course, region is there, certainly compass needle is going to deflect. Okay, now we are going to talk about this scenario that, okay, how when in a conductor, current is going to flow, how it is going to form. Moreover, magnetic field lines are getting formed. Okay, so have a look over here. Magnetic field line due to a current carrying conductor. So what type of current carrying conductor we are going to talk about? Yeah, we are saying, okay, magnetic field lines, they are getting formed. Okay, so what type of conductors? First of all, we are going to talk about straight wire. Okay, then we are going to talk about circular loop, straight wire. Current is passing through it. Okay, a loop, circular loop, current is passing through the loop. Right? From here only, no? Positive and negative. Yeah, then we have solenoid. Okay, a spring sort of a structure through which the current is passing. Okay, so these three we are going to talk about, and we are going to experience and see how magnetic field lines they are getting formed, what are its current scenario, what are the factors they are depending upon, everything we are going to see. Okay, so let's start with the first one, that is nothing but our magnetic field. Yes, due to a current carrying conductor in a straight wire. So straight wire. Okay. Now, everyone, very basic we are going to talk about. Okay. Yes, we experimentally observed this as well. So, take up a wire in which current is passing. Of course, ma'am, I am taking up a wire in which electric current is passing. So what? Yes, when electric current will pass through the wire, what will happen? Magnetic field lines, they are going to arise. Okay, of course, magnetic field lines, they are going to arise. But how? We saw that these magnetic field lines, they are arising in concentric circles. Concentric circle means, yes, the center is going to lie on the wire itself. Okay, so like this. Okay, everyone. Yeah, so this is how magnetic field lines, they are going to arise in a wire. Current is passing through it. Okay, right now I'm just talking about that how. Okay, what probably is the shape itself. I'm not talking about direction and everything. Yeah, alright, perfect. Now we are going to move forward that, okay, a current is passing through it. But what will be the strength? How much? Kids, logic, use logic over here. If I'm saying lot of amount of current is passing through my wire, ma'am, more the magnitude of the current, of course, stronger and stronger will be your magnetic field lines. Yes, the strength of the magnetic field lines will increase. Logic, right? So yes, you can certainly say your magnetic field lines, they depend upon current in a scenario. Okay, for direction, I will give you the whole thing also. Yeah, right now let's not go into that. Last thing, what will happen? See, we know that, okay, when you see in a normal scenario also, if I talk, right, yeah, the closer you will be to the conductor itself, and the closer you will be, yeah, over here to the magnetic field, yeah, the more distance you are going to take up, okay, magnetic field line is going to decrease. Now have a look. See, far away. Why? Because of course, the closeness is going to decrease when of course you are going to move far away. Magnetic field and closeness decrease. Okay, the magnitude is certainly going to decrease. So two things are very, very important. One will be current. Yeah, stronger amount of current. Second will be distance. Okay, so whenever we talk about, okay, current is passing through a conductor. Yeah, yes, the factors on which straight wire I am talking about. Yeah, so over here the factors on which my magnetic field lines, yeah, they are going to depend upon, first thing will be current. More the current, yeah, more will be the magnetic field line strength, magnitude. Okay, talking about kids, distance. How you are going to talk about distance? Yes, ma'am, distance. No, magnetic field line, they are inversely depending upon the distance. Why? More the distance, magnetic field line strength is going to decrease, drop down. Yeah. Moreover, when I say lesser is the distance, magnetic field lines are going to be close enough, stronger will be their magnitude. Okay, very logic. Yeah, last thing will be direction of current. Now this is very important. Why direction of current is important? Direction of current will only give you the direction of magnetic field. Direction of, now nobody will ask me why I am writing B over here. Magnetic field. Yeah, you want magnetic field, right? Okay, one second. If you are getting confused, let me use magnetic field lines only. Okay, magnetic field lines. Okay, but please, field lines, okay? This one would be magnetic field line. Alright? Yeah, so my direction of current will actually help me in order to find out the direction of magnetic field line. That is very important. Why? Magnetic field line require both, magnitude and direction, right? So yes, how will I find out the direction of magnetic field line? For this, we have nothing but our, right hand thumb rule. Very easy. Okay, right hand thumb rule will help me for finding the direction of magnetic field line. Simple, that's it. Okay, direction of magnetic field line, that's it. Yeah, how? You have your right hand? Okay, thumb over here is going to tell me the direction of current. Okay, and my curling fingers, they are going to tell me the direction of magnetic field line. How? This is a wire and current is flowing. Okay, now keep the thumb here and move your fingers. Can you see? Yeah, moving the finger. Okay, have a look, moving the finger over here. Now, if I draw, I am drawing a circle and yes, see, keeping here, coming out, and this one going from, see, if I say left hand side over here, of course it is coming out, the fingers are coming out, and on the right hand side, the fingers are going inside. Okay, this side out, this side inside. That is why the arrows are here. Okay, so if I draw it like this, have a look. Okay, out and inside. Can you see? This is clockwise or anti-clockwise? Clockwise or anti-clockwise? Anti-clockwise, right? So, anti-clockwise. Whenever the current is moving in the upward direction, yes, your magnetic field lines are anti-clockwise. No need to learn. Just do it with your hand. Yeah, similar way. If I tell you, have a look. Current is flowing down. What you are going to do? Thumb in the current direction. Have a look on the fingers. Right? What is it? Here, on the right hand side, curling fingers outward and going inside. So, if I draw the circle, no? Yeah? So, like this. Now, this is clockwise or anti-clockwise? Clockwise, right? Clockwise. Simple. How difficult this is? So, you can say my direction of current by using right hand thumb rule. I can find out the direction of magnetic field line. What you are doing? Direction of magnetic field line only, no? Yeah, pretty much clear. So, your right hand thumb rule is going to help you with the direction of magnetic field line. Okay, have a look over here also. Indicate the direction of magnetic field. You know the direction of magnetic field. You can talk about current also. Yeah? Okay, generally we say current is given to us. Okay, now one task for all of you, what you can do is, if wire is like this and current is here, okay, then what will happen? Have a look over here. Current, okay, curling fingers. Yeah, in this particular scenario, no, everyone, I will give you the example also, how the questions actually come up. Okay, let me share that also, that how the questions actually come up. See, right? I'm sharing that here only. So, they can tell you, they can tell you, yeah, that current is moving in a wire. Okay, current is moving in a wire, right? Current in a wire, and it is moving from east to west. Find out the magnetic field line direction. Okay, now how you are going to do this question? See, draw a wire. Current is flowing from east to west. Okay, keep your thumb there in the current direction and look on the curling finger. First of all, the upward portion, have a look here. My fingers, they are going inside the board, no? So I will write down magnetic field lines are inward. Right hand. Yeah, now keep it here. Curl, 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 curl. Yes, your fingers are coming out. So write down over here outward. That's it. That's it. This is the direction of magnetic field line. Okay. Similarly, you can draw any type of conducting wire and talk about it. Okay, everyone. Now, wire clear. Similar way, we are going to talk about circular loop. Let's have a look on circular loop. So, for circular loop, everyone, first of all, the first thing will be, yes, I will draw a circular loop. Okay. Current is flowing. Current is flowing. Alright. Now, as you can see a circular loop through which the current is flowing, of course, first of all, we know that yes, my magnetic field lines, they always occur in concentric circle. Okay, so if I will draw concentric circle over here, yes, they will look like, okay, like this, yeah. Now, you know what will happen? Of course, the concentric circles, they are going to widen up, widen up, widen up. And when you are going to see that, okay, there in the center, you are going to see magnetic field line, they are in straight lines only. Okay, they tend to be straight. Yeah, because infinite, no. Widening up, widening up, widening up. So, what will happen? Of course, after one point of time, they will become straight line only. Okay, see, have a look. Now, to concentric circle we know, closed circle, concentric circle we know. What about the direction? We know one thing, that when we talk about direction of a magnetic field line, we use right hand thumb rule. Want to use over here? Of course, let's use it. Current moving up, right? Have a look. Curling fingers. Yeah. So if I draw the arrows, have a look. Up, no. It will be clockwise, anti-clockwise, anti-clockwise. So, yeah, and here inside, 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 inside. Okay. Similar way over here, current going down, have a look over here. So, this is downwards, right? So, this is, have a look, clockwise, yeah? So, clockwise, 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 okay, okay, okay. Okay, right? Now, focus and see. When I am talking about right hand thumb rule, in order to find out what? I am finding out direction only, right? Of magnetic field line. So have a look. My magnetic field lines here in the center of the loop, they are inwards. Moreover, magnetic field lines outside the loop, they are outward. When the current in the loop is clockwise. Let me give the whole case to you again. Have a look over here. See, if I am telling you, okay, and yes, you can note this down also. Very important point. There is a loop. Yeah, two loops, let's draw. Okay, two loops. First loop, second loop. Okay. Yeah. In the first loop, the current, have a look, the current. Clockwise, anti-clockwise. Current I am talking about. Current I am talking about. Current is nothing but clockwise. Okay. In the second loop, opposite condition we are going to take. See, clockwise. I believe all of you are aware. Clockwise, anti-clockwise. Okay, anti-clockwise. This is current. Yeah, now simple right hand thumb rule only we are going to use. So, first of all, concentric circle. Concentric circles. Over here also, concentric circle. Okay. Now, understand, when I say right hand thumb rule, so yes, have a look over here onto my hand. Thumb is up. Why so current? Yes, the fingers curling. Curling, no. Curling, how they are curling? Anti-clockwise, so draw the arrows. Okay, draw the arrow. Yeah. Similarly over here, if I am saying thumb curling clockwise, right? Now look on the arrows, everyone. Inside the loop, the arrows are going inwards. So magnetic field lines inward. And over here, arrows are going outward. So outside, it's outward. Magnetic field line. Now, let's check it here also. That what will happen in the anti-clockwise scenario. Have a look. Curling finger. Yeah, curling finger. So, of course, clockwise. Okay. And these are the arrow. Yeah, anti-clockwise. Sorry, clockwise. Okay, now over here have a look. Anti-clockwise. Okay. And this one would be. Now have a look on the arrows, everyone. Here in the anti-clockwise scenario, inside magnetic field lines, they are outward. And outside, they are inward. Opposite case. Okay, there is one more case in this scenario. What people say is whenever there is a loop, and yes, in the loop, clockwise current is flowing, no? Yeah, clockwise current is flowing. They are going to certainly say that, okay, this is nothing but your south pole. It is representation of the south pole of a magnet. Okay, similar scenario in the anti-clockwise scenario, they are going to say it is going to represent the north pole. Okay, north pole. How? Let me show you that as well. So they are going to draw S, okay, like S. And with this S, have a look on the arrows clockwise. Okay, similar way over here, they are going to draw N. Okay, have a look on the arrows now. Anti-clockwise arrow. Okay, you need not go into that much depth, but if you want to, yeah, of course you can. Okay, coming back right now. 4 direction right hand thumb rule we used. Okay, we said that okay, here in the circle, in the loop also, the circular loop also current is flowing, and we can talk about that. Magnetic field lines, concentric circle, everything remains same. Yeah, so factors affecting everyone. What are the factors that can actually affect my circular loop? One will be current. Why? More the current, of course. So, more the current, more will be the strength of the magnetic field line. Okay. Then, radius of the loop. Now, this is very, very important. Now, if I will give you 2 loop, okay. This is loop A and this one is loop B. Okay. I'll just erase that portion up because I don't want, to overlap anything that was written over here. Let me make it here. I believe you can see the, size difference, right? Okay, now here. Okay, that's loop B. So, when I talk about loops, right? So, can you say that, okay, in which loop the magnetic field line, they are going to have more strength? Yes, magnetic field line, they are going to have more strength in loop A, because when we will talk about magnetic field lines and their closeness, how enclosed they are very, very enclosed in loop A. This is the reason magnetic field lines, they are going to be stronger here. Okay, so radius. Okay. And last one, direction, of course, right hand thumb rule we are using. Okay, pretty much clear. Now, when I say magnetic field produced due to circular coil or circular loop, so first thing now we are going to jot it down, okay. Yes, they are circular and they are concentric circles only in the enclosed space. Okay, second point will be near the near the center of the coil, what we saw? We saw magnetic field lines, they are almost parallel to each other. Okay, there in the center, magnetic field lines, they are actually becoming parallel to each other only. Okay, moreover, turns out to be the plane of the magnetic field line are at right angle to the plane of the circular coil. See, at right angle, certainly. Okay, factors affecting current. More the current, more will be the magnetic field line. Okay, radius, everyone. See, inverse relation. Yeah. More will be the radius, less will be the magnetic field line, certainly the strength is going to decrease. Okay, direction, third point, direction is pretty much easy. How come? Right hand thumb rule we are using, direction of current will only tell us direction of magnetic field line. Okay. Now, taking this forward, we are going to talk about a solenoid. Everyone, whenever we talk about a solenoid, no, it is a similar, spring sort of a structure in which electric current is flowing. Okay, as electric current is flowing through the solenoid, what will happen? Yes, it is a material, right? Insulated copper wire, spring like this. Okay. So what will happen? Of course, current is going to flow. Certainly, yes, magnetic field lines are going to emerge. Here, very important thing, as magnetic field lines are going to emerge, yes, magnetic field lines there in the solenoid, they follow a pattern of a bar magnet. You will see that, okay, similar to that of a bar magnet, you can see magnetic field lines emerging out of it. So if I draw, it will be like one end would be the north pole, the other end would be the south pole. Kids, the end where the positive terminal is connected, that is nothing but the south pole. Okay, negative end, north pole. So from north to south, you are going to see, okay, north to south, but internal, of course, yeah, like this, and then of course like this. Okay, so very important thing. Okay, now have a look over here. If I talk about a bar magnet also, a similar scenario. Can you see something over here? In the center of my solenoid, I can see that, okay, my magnetic field lines, they are parallel with each other. Okay, straight magnetic field lines parallel with each other. So, these magnetic field lines, what they are representing over here, that, okay, they are in uniform scenario. In uniform scenario, it certainly gives you that, okay, here they are in a uniform region created form. Okay, now have a look at the ends also, yeah, you can see closed loops and movement of the magnetic field lines taking place. So, when we talk about solenoid, the first and the foremost important thing will be that a solenoid is nothing but a substance, yeah. Basically, we don't use current carrying wire magnetic field lines. We are going to depend upon solenoid only. Okay, yeah, for the strength purposes. Okay, for the magnetic field lines also. Certainly, solenoid is the most important one. Okay, used for a lot of applications as well. So, coming back, magnetic field lines represented by straight magnetic field lines parallel and very close with each other. Magnetic field lines inside a long solenoid decreases as we move towards the end of the solenoid. Okay, certainly. Why? Because they are spreading out. Okay, so magnetic field line inside the long solenoid decreases as they move towards the end because they are spreading out with each other. When they are closer, yes, of course, the magnetic field line strength is going to be maximum and more as such. Okay, but here, as you can see, a uniformity is also maintained there in the center, as you can see. Okay, so one end of the solenoid is north pole. Which end? Of course, the end connected to the negative terminal of the battery cell. Okay, the other is the south pole, the end that is connected to the positive terminal of the battery or the cell. Yeah, now taking this information, we are going to talk about how the solenoid and the current is going to pass through a solenoid and how it will behave like a bar magnet. See the picture only. Okay, a difference? No, right? Similarity? Yes, right. How? Ma'am, magnetic field lines there in the bar magnet, they look similar to my solenoid only. So, I can say that, okay, there will be some factors and there will be some scenarios by which I can talk about solenoid. Of course, we can. Okay, talking about the first one, everyone. The strength of the magnetic field line can be increased. How can I increase the strength of my magnetic field line? First thing will be, Current, logic, current, we know current. Yeah. So more the current, of course, more will be the strength of the magnetic field line. Okay. Similar way, increasing the number of turn. Now increasing the number of turn, everyone, have a look. This is my solenoid. This is the length. Okay. Let's say this is the length of a solenoid. Okay. Over here, yes, the turns per length, per unit length actually matters. Now, in similar length, if I will draw similar length, so number of turns per length, that matters. Okay, more the number of turns of my solenoid, yes, certainly the strength is going to increase. Very important point. Okay, decreasing the gap. Why I want to decrease the gap? I want the wire to be very, very close by. Why? So magnetic field lines will be very, very close by. In close, and yes, my magnetic field lines very, very close by. Yes, stronger will be my solenoid. Okay, now last point is nature of medium inside the core of solenoid. This we will talk, and this will lead to electromagnet only. Okay, so we are going to talk about it. Certainly, I believe solenoid, what exactly a solenoid is, that is pretty much clear to everyone. Yeah, so three things, yes, current carrying through a conductor, straight wire done, circular loop done, and solenoid is also done. Okay, now if there in the solenoid only, no, I will insert a, let me say, soft iron. What will happen? When I, in the particular solenoid, looped wire, I am inserting a soft iron core, yes, it will turn out to electromagnet. Electromagnet, yes, electricity making a material behave like a magnet. So yes, have a look over here. Diagram also, electromagnet is a temporary strong magnet, is just a solenoid, same solenoid, but this wire is wrapped around a soft iron core. Yeah, have a look, soft iron core. Okay. Same. Right. Now, what will the soft iron core actually doing? The soft iron core is actually placed inside my solenoid to increase the strength of the electromagnet. Okay. Electromagnets are the magnets, they are temporary in nature. They are dependent by electric current only. Yes, if you are going to pass electric current through this solenoid, of course, it is going to form the magnetic field lines around it and then only behave like a magnet. Else it won't. So, electricity dependent. Yeah, you cannot say that, okay, every time I am bringing electromagnet, it is going to attract magnetic material. No, I believe you have seen cranes, huge cranes, scrap material, no, they are actually been taken out from the garbage by using electromagnet only. I am telling you, there is a car, okay, huge car made up of iron. Okay, I want the car to move from one place to another with the help of a magnet. Right, I am taking up a huge horseshoe magnet, putting the magnet onto the car and lifting it, easy. But in this case, if you will try to remove the magnet from the car's body, it will be difficult for you. Why so? Magnetic force, right? Very, very strong. So in that particular scenario, we prefer electromagnets. Why? Electricity is passing through the magnet, behaving like a magnet. Electricity is passing through the electromagnet, it will behave like a magnet. Now, after I am moving the car from one place to another, I will just switch off the current. After switching off the current, that material will not behave like an electromagnet anymore, temporary magnet anymore, and it will come out of the car body in an easy manner. So, electromagnet acquires magnetic property only and only when electric current is passing through it, else it won't. Right? That is why we say temporary magnet depending on electric current, else it won't. Yeah. Now, taking this thing only forward, when I say, yes, if I am telling you that, okay, magnetic field lines are there, certainly, we are talking about current, what will happen? See, there was this experiment done. Alright, so what happened was, people were like, okay, I am taking up a normal material. So, they took up an aluminum strip. Okay, hung that aluminum strip and passed electric current through that aluminum strip. Magnetic field lines arise through the aluminum strip. Okay, current carrying conductor. Now, they kept a horseshoe magnet just near this aluminum strip. All of you, they saw that, okay, this aluminum strip is actually getting attracted and moving. Okay, I won't say attracted as such, but they are moved. So, first thing is very, very clear. Yes, if a material is moving, yeah, or experiencing some amount of force in presence of a magnet, of course it is behaving like a magnet as such. But aluminum is not a magnetic material. So how this is happening? This is happening because of force on current carrying conductor in a magnetic field. That means if I am having a current carrying conductor, right, and I'm keeping it in a magnetic field, I can see an experience of force exerting onto it. Right, so we can find out this force, that okay, what force and in which direction the force is actually getting, put onto. But when we say force acting on a current carrying conductor, have a look over here. When a current carrying wire is placed in a magnetic field, it experiences a magnetic force. Okay, so the material is not itself a magnet. Yes, after current is passing through it, keeping it there in a magnetic field, it can experience a magnetic force. Who was the scientist? Yes, Andre Marie Ampere. He was the one. He suggested it. He did the experiment. Okay, so the experiment, what it showed? It showed the direction of force on the conductor. It depends upon the direction of current and direction of magnetic field. If I tell you, okay, this is the direction of magnetic field, this is the direction of current, you can talk about the direction of force, that in which direction the force will be exerted. Okay, how you can find out this force? Very simple for this. Yes, for this we use Fleming's left hand rule. Now have a look. Fleming's left hand rule for the direction of force. Very, very important. Kids know, they actually get confused. Where we are using right hand thumb rule, where we are using Fleming's left hand rule. So very clear. Yeah, right hand thumb rule will tell you the direction of magnetic field line. Yes, Fleming's left hand rule will tell you the direction of force, magnetic force. Okay, very simple. We are going to understand F force. Okay, your thumb will tell you the magnetic force. Yeah, forefinger will tell you nothing but your magnetic field, and your index finger will tell you the current. Okay, so father, mother, child. Father, okay, mother, child, like this. And yes, all the three fingers, two fingers and thumb, they should be in 90° with each other. Okay, left hand, so left hand, use your left hand only. Okay, yeah, pretty much easy. Or you can use FBI also. F stands for force, B stands for magnetic field, now you know, and I stands for current, FBI. It's totally up to you. Or father, mother, child. Right? Now, everything should be mutually perpendicular to each other. Now, let's see how we are going to use it. So, let's have a look. Everyone, okay? So, this is the first case, okay? Now, I'm telling you. This is nothing but my magnetic field, and this is my current. Okay, current. So, keep your finger. Magnetic field given to you, current given to you. Where is your thumb pointing? Outwards, right? So, the force direction, magnetic force direction will be, magnetic force will be outward. Magnetic force will be outward. Thumb will tell you. Easy? Right? Let's take one more. Okay. Now, let's say that, okay, let's take up this case. Yeah. Magnetic field, okay, current. So now, magnetic field, okay, current, where is my thumb pointing? Inside. So, my magnetic force, inside. Easy. Similarly, anything they can ask you. Yeah, you can use any of the other scenarios also to talk about it. Okay, pretty much easy. Now, we are going to take up a question. Have a look. So, find out the direction of magnetic field. They want the direction of magnetic field. Everyone, force is given to you. Yeah, and current is given to you. So, that means, have a look over here. Force is given to you and current is given to you. Okay, so direction of magnetic field, everyone, outward. See, have a look. Yeah, so magnetic field will be outwards. Have a look again. Force, father, mother, child. So yeah, outward. Easy. You can do ample of questions like this. Alright, moving ahead. Okay, fine. Now we are going to talk about the last topic. Yes, your rest of the topics, they are exempted from your syllabus. So of course, we are going to talk about domestic electric circuit. At our houses, electricity comes, right? So there is a proper scenario, proper manner. So first of all, we will talk about the 3 wires. Okay, have a look. Okay, so 3 wires involved in our domestic circuit. That means your domestic electric circuit at our houses. One will be live wire, other will be neutral wire, the third will be earth wire. Kids, have a look over here. Earth wire, green in color. Yeah. See, right now, no, you will say that, ma'am, I have yellow wire, blue wire, pink wire also. Kids, these are the standard colors. And yes, we should follow. Okay, earth wire, green in color. Live wire, red in color. Neutral wire is black in color. Okay. Live wire, yes, it is the wire. It is a positive conductor that helps to break the circuit when excess current flows through the circuit. Certainly, you say when live wire is there, right? Okay. So, yeah, live current is going to flow through it. Okay, talking about neutral wire, yes, it is a negative conductor, of course, 0 volt. You require a potential difference, no, for the current to also move. So over here, for live wire, you have 220 volt to 230 volt. Okay, then earth wire is the protector. All of you, whenever we talk about earth wire, it is a protector. At times, on our devices, static charges, they get accumulated. So when you are going to touch it, right, they are going to flow through you and you might get shocked. So earth wire will take up these extra charges, dump it onto the earth. Yeah, so yes, earth wire, have a look, live wire is going to move through the electricity board, then electricity meter, and then to all your appliances in parallel form. Okay, neutral wire also, electricity board, meter, and through the distribution board and all through the appliances. Parallel scenario. We know about this, right, at our houses. Now, last one, earth wire, everyone. Earth wire is directly connected through the devices only. Okay, no point of fuse and everything, right? We are concerned with appliances only. Okay, now let's talk about few more things. See, pole fuse, electric meter, and distribution board. Very easy. So after the live wire, right, you have electricity board fuse or your pole fuse. So what will happen? Before electric lines, they enter your house, the agency supplying the electricity, they will place a fuse. Okay, fuse, everyone, a safety device, yeah, pole fuse, company fuse, okay, in the live wire itself. Have a look in the live wire itself. Okay, the current rating of this fuse depends upon the load sanction. So yes, if a lot of huge amount of current is flowing, of course the fuse will melt and your home and everything would be safe. Okay, then electric meter. After the company fuse, the cable is connected to the energy meter, electric meter. Yeah, this electric meter will only record how much electricity you are consuming. Yes, over here, have a look, consumption in kilowatt hour. Yeah, then distribution board, yes, the power lines coming from the main switch are taken to the distribution board. Okay, and it is from the distribution board that the wires go to different parts. So the distribution is nothing but, have a look over here. Yeah, containing distribution box certainly contains the main switch, fuses and everything for each circuit. Okay, this is your basic diagram of your domestic electric circuit. Now, last 3 very important definitions, they are overloading, short circuiting and earthing. So everyone, overloading. What will happen? Overloading. So when you are going to use a particular plug, yeah, attach lot of appliances onto it, what will happen? Lot of current is going to go out of it, right? So certainly overloading is nothing but a number. When a number of electrical appliances, they are used at the same time and draws huge amount of electric current. So of course it is going to hamper, no? Yeah, huge amount of electric current at the same time, right? Okay, so this causes overloading. Even when number of electrical appliances, they are connected to the same electrical socket, overloading takes place. Yeah, overloading very easy. Short circuiting. Short circuiting will be when at times neutral wire comes in contact with the live wire. What will happen when neutral wire will come in contact with the live wire? Zero resistance. So huge current will flow and your device will melt. Moreover, device is melting, lot of heating. Certainly it might get caught fire. Okay, so short circuiting will be when your live wire comes in contact with the neutral wire, zero resistance, huge amount of current drawn, huge amount of heating, certainly device will melt or get caught fire. Okay, last thing is nothing but your earthing. Talking about earthing, everyone, Simple. It is a process we do in order to save ourselves from getting a shock. Okay, what we do is we place a earthing wire and we dump all the extra charges getting accumulated on your electrical appliance there onto the earth, because earth is a huge dumpster of charges. You can dump it onto it. So earthing is a process of protecting against unwarranted spikes and bouts of electricity that can cause damage to life and property. Okay, so this is the symbol of earthing also. Clear everyone? Right, so we have completed our whole chapter there in a single go. I hope all of you understood. Keep on practicing, keep on revising. Any doubts, anything you want to share, share it up there in the comment section. Thank you so much all of you.